Today we start Chapter 7, which is on trees and networks. Chapter 7, Section 7.1 is just about the basics of a tree. So the first thing we need to talk about is, well, what is a network? Okay, so we're still sticking with the whole theme of graphs. A network is any connected graph. Remember, in order for a graph to be connected, there has to be lines or edges that connect each one of the points, dots, vertices, whatever you want to call them. In the tree diagrams, the vertices of the network, we often call them nodes, N-O-D-E-S, or terminals. And they represent objects. So there has to be something there, like a light pole or a person, okay? Your edges of your networks, we now are going to call links. So, all same concept as to what we've been doing, it's just we now have new vocabulary. This chapter's theme is we're finding optimal, okay, so there's that word again, networks that connect a set of points. So we're still trying to find the fastest or the smallest way to connect points. Our goals of this chapter is number 1, connect all the terminals, again, which is the same thing as your vertices. This time, connect. We do not have to create a Hamilton path or a Euler path or circuit. So we've got no Euler, Hamilton, path or circuit. And again, because we're looking for the optimal network, we're trying to find the total cost length of the network that's as small as possible. Okay, so here's an example of something we're going to look at in this chapter. The weighted graph represents a system of roads connecting buildings of a company's headquarters. The company is planning to upgrade its fiber optic cable through underground lines connecting its servers. The weights represent cost in millions of dollars to upgrade these cables between each building. The goal for the company is to find a network that utilizes the existing network of roads and connects all the buildings together. In other words, has the least cost. So these are the types of problems that your electricians are going to look at. City plumbing, okay? They don't want to spend a lot of money in order to connect different things. So we've got a couple key terms we've got to look at here. The first one, excuse me for 1 second here, guys. This is going to drive me insane. Okay, hopefully that's done now. Of course not. Why would it ever want to be done? Okay. All right, so some key terms here. The first one is a subgraph. Anytime that we create a subgraph, your edges have to come from the original graph. So If there's no line that connects point D and C, you cannot draw an edge there. They all have to come from the original picture. Your second term here is a span. This must include all vertices. So if there's 5 dots in the original graph, there has to be 5 dots in a span. If there are 8 dots in the original graph, there has to be 8 dots in a span. And the last one is minimal. This is when the total weight of the network must be as small as possible. Again, we're looking for that optimal answer. We're looking for it to be small. So let's look at some examples that explain these vocabulary words. So your original graph is on the left here. We have 6 vertices, A, B, C, D, E, and F. Okay. And we've got 1, 2, 3, 4, 5, 6, 7, 8 edges, it looks like. Okay, so example number 1 says we want a subgraph that has 4 vertices and 6 edges. Remember, our vertices, we don't have to have them all because this is a subgraph, not a span. So we can minimize the amount of vertices, but remember, all of our edges have to come from the original graph. So we need 6 edges from the original graph in order to draw these using only 4 of the dots. So looking at the original graph, what section of the graph has 6 lines connecting 4 dots? Well, you're not going to look over at this left-hand side here. There's only 2 edges that connect these. Okay, even if you expanded over to this part, there's still only 3. So what we're going to want to look at here, let me erase this real fast, is we're going to want to look at this part. Okay, you've got 4 dots and 6 edges that connect it. So a subgraph of the original would be these 4 dots. So we want B, C, E, and F. And we want all 6 of the edges that they use to connect them. So that would be a subgraph of our original. Example number 2. This time we want a span that has 5 edges. Okay, remember, a span has to have all 6 vertices because there were 6 vertices in the original. So we need all 6 vertices. Oh. Sorry guys, my computer is not working with me today. Okay. So we want 6 vertices. And remember, this has to be a connected graph, so we have to connect all of these dots. We cannot leave one that's off to the side and not connected. Okay, so we need to connect these in 5 lines. You have a couple different options here. I'm going to do the first one in green. So I'm going to draw this and this that connects these 3 at the top. That's 2 edges. Here's 4 edges. Now, I've got a couple of different options here. I can drop this line down like this. That's a span. It has all 6 dots and 5 lines. I could have done the same thing, connected these ones, and instead of using that center line, I could have used this line. I could have also gone here, here, and instead of using one of these straight edges, I could have used a diagonal. And there was one other option here that I can show you. I could have went here, here, and here instead. So depending on which one would technically be optional once we add numbers, that would change the span. Okay. All right. Example 3. We want a subgraph that has 5 vertices, and we only need to connect them using 4 edges. You can pick any 5 vertices you want. Okay, let me get a black marker here. So I'm going to do A, B, D, E, and F. I'm going to leave out C. Remember, our only rule for a subgraph here is to connect all of them using 4 lines. So, if this was A, and this was B, this was D, E, and F, there was only one choice to connect A and B, so there's one edge. B and F was connected, that's 2. Here's 3 edges, and here's 4 edges. You could have used the middle line that connected B and E instead of the line that connected B and F. You could have used the middle line that connected B and E instead of connecting E and F. Okay, there are a lot of different options here. Okay, span of 6 edges. Keyword here, span. Span, that's our key word here. So span means I need all 6 of my dots. I need all 6 nodes or terminals. And this time I need to connect them using 6 edges. Any 6 edges you want. Okay, so I know I need to use these 2 because it's the only way to reach out to A and to D out here. Okay, those are givens. B, C, E, and F. Okay, I don't have another choice there. I have some options for the rest of the 4 though. I just need to leave out 2 of the lines that connect that big square of B, C, E, and F. So I could use the diagonals and just a random 2 edges. Example 3, subgraph of 6 vertices and 5 edges. Notice though, 6 vertices. So this is also a span. Because it contains all 6 vertices, this is also going to be a span. 4, 5, 6. Okay, this time I only need 5 edges though. Again, I need to use these 2 edges here. I really don't have a choice because in order to connect A and D, those are the only 2 edges. And because this is a subgraph, I have to use the original edges. I cannot make up any new ones. Okay. And I need 3 other edges to add in. So as long as I connect to C and F, we're good. So let me connect B to C, B to F, and B to E. Okay, looking a little deeper, specific types of networks. First thing we've got to look at here is a tree. A tree is a network remember, this has to be a connected graph. With no circuits of any length. So remember, a loop is a circuit. So if our graph has a loop, cannot. If I can travel one dot and go the whole way around and go straight back to that dot by tracing edges, I have a circuit. So that is also no-no. So all we're going to do in the first 8 examples here is we're going to identify, do we have a tree? And why do we have a tree and why do we not have a tree? Okay, so let's take a look at these examples here. Okay, in A, we've got 2 graphs that look like Ys. Tree or not a tree? This is actually a no. This is not a tree. Why is this not a tree? It's not connected. Okay. It's not connected. If I would have a line that would connect this somehow, some way, somewhere, then yes, it would be a tree. But remember, in order for it to be a tree, it has to be one big piece. It cannot have small pieces. Take a look at B. B is a yes. There are no circuits of any length, and everything is connected here. Graph C. Graph C is a no. We have a nice big circuit here. So there is a circuit. D. D is a yes. Okay. Take a look at E. E is also going to be a yes. Graph F, however, is going to be a no. There are circuits. There are actually several circuits. Okay, you've got that one, you've got another one here, you've got another one here. You can actually call this entire huge thing a circuit. It's So you have multiple reasons to call that one a no. G. G's kind of tricky. But remember, just because they cross here does not mean that there's a terminal there. So there actually is no circuits in this one. So yes, this is a tree. Because if I would leave here and trace this, I get stuck way out here. Now, if for some reason that these two were connected, that would have caused a problem. The last one here is also going to be a no. Now, the circuit is very hard to find here because it doesn't technically look like a circuit, because it's kind of a circuit and then it's twisted. But you've got this circuit here that causes an issue. Okay, so we're going to look at these graphs and come up with some conclusions or some observations from them. Observation number 1, is there a relationship between the total number of edges and vertices in any tree? Okay, so what we want to do is we're going to go back and we're going to look at all the ones that we called trees. Let me pick a different marker color here. Okay, so we're looking at vertices and edge relationships. How many vertices are in B? Well, let's see. We've got 1, 2, 3, 4, 7, 8, 9, 10, 11. We've got 11 vertices, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 10 edges. Okay. Take a look at D. That's our next tree. Vertice, edges. 1, 2, 3, 4, 5, 6 vertices. 1, 2, 3, 4, 5 edges. Some of you have probably already seen the pattern happening here. It's okay, we're going to do them all. Vertices, 1, 2, 3, 4, 5, 6, 7 vertices. 1, 2, 3, 4, 5, 6 edges. And our last one, 1, 2, 3, 4, 5, 6, 7, 8 vertices. That's one big line here in the middle. 2, 3, 4, 5, 6, and 7 edges. Okay, so our observation that you should have come up here. Is there a relationship between the total number of edges and vertices in every tree? Absolutely. So this is a yes. There is one more vertex. Then edge. Or we can say edges are one less than vertices. Both statements mean exactly the same thing. In chapter 5 and 6, we learned a special term that represents what we call these edges. Actually, I think the best one to look at here to see if we can come up with a vocabulary word is D. So, what would you consider each one of the edges in graph D? Think about what happens if I remove one of those edges. That makes my graph disconnected. So the vocabulary term that we learned here in the last 2 chapters was this is, oops, not that one. They're bridges. So every edge in a tree is a bridge. If I'm able to remove it and it disconnects the graph, I must keep it. Okay, our next vocabulary term, spanning tree. A subgraph. That connects all vertices. And has no circuits. So, in ultimate terms, we're trying to create a tree from our original graph. So, let me get my black marker out here. I'm going to draw several of these. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Because there are several different ways to do this. So I'll give you a couple of examples here. Okay. All right, let me pick a color here. All right. Remember our rule. If I have vertices, 1, 2, 3, 4, 5 vertices, how many edges would I need? Look at our vocabulary. Edges are 1 less than vertices. So if I have 5 vertices, that means I need 4 edges that connect these points. So I can do something like this. A connects to B, A connects to C, C connects to E, E connects to D. 5 dots, 4 edges, I have a tree. I could have also done something like this. As long as all of my lines come from the original graph over here, I'm good to go. Remember, you just cannot draw any new edges. This would help if I select the eraser. Okay. Try a couple more on your own and see if you can come up with it, and then I'll give you mine. I did this one. And I did this one. Any of my 4 choices, or maybe one that you came up with that I did not, could be an answer to this question. And this leads us into the last part of this section, which is the properties of a tree. So, property number 1 says, in a tree, there is one and only one path that join any 2 vertices. So, if you're told that there's one and only one path joining any 2 vertices, the graph must be a tree. Well, we saw that up here. There's only one path that connects point A and B. There's only one path that connects point C and D in this graph. Okay. Property number 2. In a tree, every edge is a bridge. We discovered that. That was one of our observations. So if they tell you that every edge of a graph is a bridge, then the graph must be a tree. And finally, property number 3. If the tree has n vertices and n minus 1 edges, it's a tree. Remember, your vertices are always one more than edges. So if your vertices are represented by n, then your edges are represented by n minus 1. If a network has n vertices and n minus 1 edges, it must be a tree. So this leads us into the problems that everybody hates. Okay, you have to think about these before you answer. So, number 1, G has 4 vertices and 3 edges. In order for this to be an always, it has to satisfy each one of the properties. So, G has 4 vertices and 3 edges. Does that satisfy property 3? N vertices, n minus 1 edges. Yeah, okay. Property number 3 is satisfied. Property number 2. Every edge is a bridge. Does it say every edge is a bridge? No. Because property number 2 is not satisfied, but property number 3 is, this is going to be a sometimes. If you have a sometimes, draw an example that represents a network, a tree. Okay, so give me an example that looks like a tree and one that would not. Okay, so for example, you're going to do something like this. We've got 4 vertices, so this one's going to be a tree, and this one's going to be not a tree. Okay, so there's 4 vertices. One, 2, 3. That one represents a tree. 4 vertices, 3 edges. That one's not a tree because this is connected and this is not connected. Okay, just because they're side by side, we're going to actually look at number 5 as well. So, number 5, G has 10 vertices and 9 edges. Well, we're back to that same problem. Yes, we have one more vertices than edge, but again, it doesn't tell us whether it's connected or not. Okay, so this is also going to be a sometimes. This one's going to be kind of hard to draw here. We don't have a lot of room. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 10. Okay. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this one's a tree. This one here, not a tree. 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, the one on the left is all connected. The one on the right is not. Okay, take a look at number 2. G is connected with 4 vertices and 3 edges. Okay, your key word here that's going to make this one always is the word connected. Okay, you've got your 4 vertices and 3 edges. Okay, so that matched what happened in number 1, but this one has this key word of it being connected. So because that has that keyword connected, this is an always. Take a look at number 6. G has 10 vertices and 11 edges. Remember our rule with vertices and edges. Vertices always had to be one more than your edges, or your edges had to be one less than your vertices. Because this doesn't happen, this is a never. On the test, the only time you will have to draw me pictures is when you have sometimes. If it's an always or never, you just need to tell me always and never and move on. Okay, almost done. 3. G has 5 vertices and 5 edges. Again, your edges should be 4 here in order for this to work. 5 does not work, so this is a never. Edges still have to be 1 less. G has 12 vertices and 11 bridges. Whenever they use that vocabulary word, bridges here, that means it's connected. This is an always. So the only time you get a sometimes is when they're not specific, like they were in numbers 1 and 5. Okay, it doesn't say bridge and it doesn't say connected. Okay. Number 4, G has 5 vertices and 4 bridges. Okay, 5 and 4. Remember, bridges is another word for edge. It's a specific word for edge. So this is 4 is 1 less than 5, and they're specific. They tell us it's a bridge. So this is an always. And number 8, G is connected with 8 vertices, and every vertex has a degree of 7. Think of what that means for a vertex to have a degree of 7. Let me draw you a picture here so you can kind of visualize it. So we've got 8 dots. 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices, and each one of these has a degree of 7, which means there are 7 lines that come off of each one of these dots. So we've got 1, 2, 3, 4, 5, 6, 7. This one has 1, 2, 3, 4, so on and so forth. This is a never. In order for this to be a tree, can have no more than a degree of 2. Your homework for tonight is going to be page 265 in the book. numbers 1, 2, and 3 through 7 odd. Okay, so you're only doing 3, 5, and 7. Please skip 4 and 6. And I'll see you back here tomorrow for section 7.2.